This is one of the most informative meetup that I have been in the recent time. So today, what we are going to do now is we are going to take a deep dive into how these models are trained. How many of you are from machine learning background? Oh, almost everyone. How many of you have trained any model, maybe in a laptop or anywhere? Pretty good. OK, awesome. So what we're going to do for next 20, 30 minutes is we'll try to see how models can be trained at scale. And we will see how we can use Ray, which is an open source framework. Have you heard of Ray? Anyone of you heard of? OK, very few of you. Yeah. So we'll just learn about Ray and how we can train such models. Okay. So before that, let's understand why we need to distribute our training. We can train our model in our laptop or Google Colab. Why we need to distribute our training? Anyone? Any guesses? Why we want? And when I say distribute, that means not in one GPU. I need 2 GPUs, 3, 4, or hundreds. Yes, sir.
You have more data than you can.
Yeah, we have more data. Yeah. Speed. Yeah. Speed, more data, and maybe the model size. Right? So that is not small enough to get consumed in one GPU. So let's consider that model and data, right? And as Jimmy mentioned, the speed. So let's assume for now, for next 5 minutes, that this model and data we can store in this GPU. Okay, so that GPU has enough memory to take that model, the whole model, and the data. Now let's say I have more data now. Right? Yeah. So now let's say we have more data. Can we now continue this training like before? No, right? Because we have to do it one batch at a time. So it will take, let's say, 4 hours to do this. Previously, it was taking 1 hour. Now it will be 4 hours. Now let's consider that we want to just speed up things. What we can do is we can take 4 GPUs and we can parallelize this. Right? So 4 microbatch of data will go, but there is one single model. The model is the same. What we are doing is we are just copying the model in all the GPUs. With this setup, can we do the training just like before? We cannot. If we do that, then we will find 4 different models at the end of the day. Right? So let's see what special that we need to do. To do that, first we have to understand what is there inside the model. Right? So inside the model, we have the parameters. So whenever you hear 10,000 parameter, 10 billion, 1 trillion parameter model, that is the parameters. Right? Then we have the gradients, and then we have the optimizer. Right? So the optimizer is just almost the double of the parameter. Can anyone guess why? The optimizer, that blue, it is almost double of the green block. The reason is we considered Adam as an optimizer. So for every parameter, you need 2 trainable variables. And that's why it is exactly the double. So let's say if you have a model with 100 parameters, and if you use an Adam optimizer, so Adam is one of the optimizer. For every parameter, you need 2 parameters for that. So that's why it is just the double. So since it's the same model, we will have the same model copied. So now let's see what extra we have to do. So in the forward pass, do we need to do anything? We can have 4 microbatch. All of those 4 microbatch can go through 4 GPUs at the same time. Right? All good. Now comes the backward pass. Backward pass, once that is done, what we will have is we will have the gradient across 4 different GPUs. Right? All are different gradients. Why they are different? Because they were trained on different batch of data. Now we have to update the model. Can we update the model? At this point, at this stage, can I just go and update the models? No, right? Because if I do that, then there will be 4 different models. At this point, I have to communicate across all different GPUs. And that is what we do with, let's say, all reduce primitive. And who is giving me this all reduce primitive? It is coming from the backend GPU provider. So if we use NVIDIA, that NECL backend will take care of all of that. Now, while this is happening, there is no computation happening, right? So this is, it's not a waste, but there is no matrix multiplication happening in the GPU because they are communicating to each other. But that's still okay, right? Because we are speeding up things. It's just that we are paying this tax of communication. And once this is done, we now have the updated gradient, which is nothing but the summation of all the gradients. Now we have the same gradient in all the GPUs, and we already have the optimizer, so we can update the model and then go with the next 4 microbatch. Okay? With me so far? This is what we called distributed data parallel. Okay? Now let's say, in this example, what we thought, or what we considered, is that this whole model can fit in the GPU. But what if the whole model cannot accommodate? What we can do? We can shard the model. The model has 3 components. There are different ways that we can shard. What is the first thing that we would like to shard? If you look at these 3 things, what you want to divide at the first place? Optimizer. Why? Because that is the biggest chunk, right? So if we do that, we will keep the model parameters the same. It's just the optimizer will get sharded. Now, I'm not going through the backward pass and forward pass for this, but the common sense says that now we will need even more communication, right? Because now, this GPU contains only the first 25% of the optimizer. This GPU has the second 25%. So you cannot just do the model update just like that. So you need to do more communication. But this is what we called 0-1. Have you heard of this? 0-1, zero redundancy optimizer. So this is what we called 0-1. But let's say it is still not enough for one GPU, right? So this model is so big that you cannot even have this in one GPU. What we can do? We can shard even the gradients. So in this case, the communication will be even more, right? But when you go to the implementation, you will see that 0-1, 0-2 have a similar communication tags because of the implementation intelligence. 0-1 no one uses. This is what we called 0-2. Okay. Can we optimize even further if the model is even more bigger? Yes, right. And I hope you get the idea of where we are going, right? So now we can even shard the parameters. And this is what we called 0-3. And in few of the implementation, you might have heard of FSDP. Right? So FSDP is just an implementation difference. The underlying technology is the same. One is from Microsoft, and this is for PyTorch or Meta. Okay. So, okay. Before I go ahead, can you tell me now, in FSDP or 0-3, can everybody do forward pass in the first place? Yes, no, no. Because every GPU just have the 25% of the model parameters. So you can think of it like this. So let's say this has only the first layer. This has the second layer, like that. I'm just intuitively giving you an idea. So even for the forward pass, they have to first communicate and make sure that the first layer is there in all the GPUs. So every GPU should have some buffer memory which can accommodate to make that one layer, right? So the point I'm trying to drive here is, no matter what you choose, they all are data parallel. Why they all are data parallel? Because each GPU still computes the full forward pass and the backward pass. It's just that the way that parameters are stored, they are sharded. It's just like, if you're not from this system side, imagine that I live in a 2-bedroom apartment, but let's say I invite 20 people, and we have a plan to have breakfast, lunch, dinner together. They can come for breakfast, have food, and then please, you can make your way, right? Because they cannot stay in my house in that 2-bedroom with their luggage and everything. So every time we are having the lunch, breakfast, dinner, they all can come. That is what happens whenever you do a forward pass. Everybody need to talk, make sure that they have that layer at that point in time. Once that is done, you discard everything and go ahead with the next thing. So everything is happening in our house, but they are not staying or living in our house, right? So that's the intuition that you should get, that in all of this, I'm just sharding the parameters in a smart way so that the model can be accommodated in the model, in the single GPU, but the training is happening in a distributed fashion. Can we even scale further? Let's say you cannot even do this forward pass in one GPU. That means the data will go from here, then go to the second GPU, then third, and then fourth, and here only you can calculate the loss. It can happen, and that is what most of the very large models are trained with, and there are different techniques: tensor parallel, pipeline parallel, expert parallel, and so on and so forth. Does that make sense? Right? So this is how the distributed training works at its core. Now, how we can do this? I'll quickly go over this. So we are going to show you how you can train it with Ray. So what is Ray? Ray is a unified compute engine. Forget about that AI ecosystem, but you can think of it like if you have written any Python code in your laptop or in your desktop, now it is working fine. Now you want to scale it to, let's say, 10,000 machine. How will you do that? Ray can help you with this. How to get started? You can just do pip install. And what you get is Ray Core. That is the core engine. And it can run on any hardware or cloud provider. And this is how it can scale. So these are very simple two functions. We are creating the embedding from here, creating the embedding again, and then doing the similarity search. If you run it in my laptop, then it will be in a single thread, one after another. Now, if I have to scale this, I can just decorate it with an array. And what happens is, now this becomes task. Okay? And see this, here they were returning value. Now you have to call it like dot remote, and then you pass the value. And what happens is, you get a pointer. You don't get the actual data. You get a pointer. And so that these two execution can almost happen at the same time. And this will, if you want to get the data, you can just say Ray get and then the reference. It's basically a pointer. Now what happens here under the hood is your first function call might happen in one CPU or one GPU in the cluster. This will happen in another CPU, in another GPU, wherever you want. And this will happen in somewhere else. So that's how you can scale. And you can define whether you want this function to be executed on CPU, GPU, TPU, or whatever. So that's about classes. I don't want to go through this. It is the same illustration. But this is stateless. What about stateful? Because in the previous example, it just executed the function and then got it done. There is no relation between two function call. So for stateful, you will do the same thing, but with a Python class. In this case, the state would be instantiated here within your constructor. But the way that you will call it, exactly the same. So the point here is when you use Ray Core, you can actually distribute any application. It has nothing to do with AI or ML. But what the creators of Ray thought was there are a lot of different AI workloads that we have, which has a certain semantics. You cannot expect every developer to do a decorator and then change the code and all this. And that's why they came up with different AI libraries for different AI workloads, for serving, training, reinforcement learning, and so on and so forth. Okay? And to install all this, you can just do pip install and all these libraries. Not a big deal. And also, it has an integration with VLLM and all of that. So now, whenever you're operating at this layer, you have to use those decorator and make it scalable. Whenever you are applying in this layer, you don't have to do all of that. And that is what I'm going to show you at the end, where just like if you use pandas on NumPy, what you do, pd.read CSV, read JSON, whatever it is. So exactly now, you can do this with Ray data, and under the hood, it will create those actors and tasks, whatever it is, and it will just scale in your cluster. You don't have to be a distributed system expert to learn about fault tolerance and all of this. So now let's try to see how we can do one such distributed training using PyTorch and Ray. Okay. So before I get started, PyTorch is the core engine which you will use to train the model. The logic is still in the PyTorch. What Ray will do is it will just scale it across multiple machines. Now with PyTorch also you can do distributed training, but it mostly works pretty good when all of your GPU are in one physical machine, within one GPU, physical box. The moment you scale across two physical box, then it gets a little tricky. Right? So, and that's where you may like to use Array. So this is how you will do a typical PyTorch distributed training. You don't have to read this. I'll just walk you through. At the beginning, we have to do the setup where you have to tell PyTorch that, hey, now this code you need to run in multiple GPUs with the backend as Nickel, so that all reduced communication and all of that is taken care. So that's why this is an extra thing that you have to do when you are running in a distributed fashion. Once that is done, you have to define how you want to do the training using FSDP 01, 02, whatever it is. You define that. And then you have to have a different data sampler. Previously, when you are just running your training in one GPU, what you used to do, you just have to create a data loader and create the data set, have the data loader, and run the training loop. Now with distributed training, if you remember, we had 4 GPUs. So we want that first GPU gets the first batch, the second GPU gets a different batch, not the same batch. There must be somebody who should tell PyTorch that do it this way. And that is what this distributed sampler does. It makes sure that all those micro batches are different. And then you start the training loop, and the way that you will execute this is using torch run. Now, if you compare this with Ray train, how this changes, you don't have to do all of this. All you have to do here is you have to wrap the model using prepare model, and you have to wrap the data with prepared data. Both of this are coming from ray.train. And once this is done, you have to thread this together with torch trainer, which will take your training code and the scaling configuration, because you have to tell Ray that how many GPUs that you want and how you want to scale. That's all. And then it will just scale in your cluster. So let's see how it works under the hood. So you have your training function. This is the pure PyTorch code, which is running probably in your laptop or in any virtual machine. And these are the configuration details. And this is together, it is the array train. And you will import torch trainer. You will import all these configurations from ray train. And then you will thread all this together using this torch trainer driver. And after that, the moment you do trainer.fit, it will just scale across multiple workers. And why it is 4? Because in the scaling configuration, we have given 4. Right? That's all. Right? So that's how Ray train works. I don't want to go through this demo because it is the same thing what we just saw. But I will just show you quickly how this looks like. So, yeah. So if you see this, so this is the main function. I just have a training function, and this is the model. And this is the regular model. Let's say here it is ResNet, but imagine that you have some model, right, from HuggingFace, or even if you are pre-training, that is your model. What you would do in the main function, if you see this, what I'm doing, I'm just initializing Ray, and I have this torch trainer because I'm wrapping a PyTorch model into Ray. And this is the function that I have, and this is the training configuration, this is the scaling configuration, and this is the runtime configuration. Runtime configuration is basically for checkpointing and all. And the main thing is this training function, and if I just open this training function, everything is same. It's just that you are now wrapping your data loader with prepare data loader, and this will take care of batching and all of that. And you are wrapping your model with prepare model wrapper. That's all. Right? So these are the two things that you are doing, which is making your code go distributed across multiple machines. And here, the scale that we are talking, it's not just 10 GPU or 20 GPU, it's like 10,000 GPUs, 20,000 GPUs, like that. So we were just talking to one of the customers, Cursor, who just launched one of the model, right, a few months back. So they have been training that with tens of thousands of GPU. Okay, so that's about me. So if you want to learn about Ray, you can just go. It's an open source project, yeah, and this is a GitHub, which has the code. And lastly, I guess I have this. So this is a very, very long blog. If you are interested, you can have a look where we go to the little bit on the math side as well, if you are interested. If you want to know how distributed training works, you may like to check this. And yeah, that's all from my side. Thank you.